This video is on density. Density is defined as the mass divided by the volume of a sample of material. Capital D equals lowercase m over capital V. So your unit for density will be a mass unit divided by a volume unit. Here is a table which we'll use a little bit later. Different densities of different materials. So water, which is a common one that you should know, is 1 gram per cubic centimeter or 1 gram per milliliter. And then we have just a couple others, iron, gold, and ethanol, which you do not have to memorize. Specific gravity. That's really important when you're talking about kidney function. And the formula for that is you take the density of a substance, which we know is mass over volume, and then you divide by the density of water, which again is 1 gram per milliliter. So pretty easy formula to use. Urine specific gravity has a range from 1.002 to 1.030 in healthy people. Notice that specific gravity is unitless, and that is because when you are dividing two densities, let's say you have gram per milliliter divided by gram per milliliter, they would cancel out. So it is a unitless value. Notice you don't see any units on those numbers there. So here is an example. 5.7 milliliters of a patient's urine has a mass of 5.98 grams. Is this within the normal range for specific gravity? So to use that specific gravity formula, first we have to find the density of this patient's urine. So that is m over v. The mass would be 5.98 divided by 5.7. Using significant figures, we should have two significant figures there. So that should turn out to be about 1.0. Actually, because we're going to do a specific gravity part, we would not round our numbers yet. Remember, if you have multi-step problems, you wait till the end. So that is the density of the urine. So to do the specific gravity, we would take that number and divide it by water's density, which is 1 from that top table. And obviously, when you do that, now using sig figs as a final answer, this guy has 3 sig figs. This guy has much more than that, so we go by the lowest, which is 3. We get 1.05 unitless number. Is this within the normal range for specific gravity? 1.05. If we look back here, you can see 1.05 is over here somewhere. That is not within the normal range. That is higher than normal. A piece of unknown metal has a mass of 71.1 grams and a volume of 9 cubic centimeters. Use table 1.4 to identify the metal. So that was the table at the top that gives us different densities. So we have to find the density. So when we plug our information in, we should have 2 sig figs. So we have 7.9 grams per cubic centimeter. And if we look at the top, what is 7.9 closest to? That would be iron. So dosage calculations. These are ratios. Prescribed dosage is a conversion factor. So this is milligrams of the drug that you're prescribing or taking per kilogram of body weight. That's important. So for example, if you have a dosage of 8 milligrams per 1 kilogram, that indicates that the patient should receive 8 milligrams of the drug for each kilogram of body mass within a 24-hour period. So per day, they should have that. So you would have to find out their weight put it in kilograms and do the math that way. So again, these are all ratios. So here is an example. Ampicillin, an antibiotic, is prescribed for a child weighing 63 pounds at a dosage of 20 milligrams per kilogram of body weight per day in 4 equally divided doses throughout the day. Express the dosage as a conversion factor. So if we want that conversion factor, it is given to us in the problem here. So that would just be 20.0 milligrams of ampicillin. We should name the drug per 1 kilogram body weight. You can flip the numerator and denominator there, right? Just like there's 4 quarters and $1. $1 is 4 quarters. So you can flip that. There's nothing wrong with that. Part B here says how frequently should the medication be given? And it says right here in 4 equally divided doses throughout the day. So 4 times daily. Or if we split that into hours, it would be what? Every 6 hours. And now for the math part of it, how many milligrams should be given to the patient at each administration? So we would write down our given thing. We're going to do dimensional analysis here. So our given thing is we know the child weighs 63 pounds. 63.0 pounds. Put that over 1. Now we don't want to work with pounds. We want to work with kilograms. So crisscross units. 1 kilogram, 2.205 pounds. Notice your pounds cancels. We're still crisscrossing kilograms of body mass and then the milligrams of ampicillin. And we know that's 20.0 and then 1 kilogram. That's our dosage. And that equals, I'm not rounding or anything yet. I'm going to write the full number. And that's how many milligrams per day that the child should be given. But notice in C it says at each administration. And we know that there's 4 administrations, 4 doses throughout the day. So I'm going to do another little dimensional analysis thing here. Milligrams per 1 day. Now, we didn't do this with dimensional analysis yet, but I want milligrams in my answer. So I'm not going to crisscross my milligrams down. I don't want that to cancel. I'm going to worry about the days. So since day is at the bottom, I'm going to bring day at the top, and I can relate days and dosages. And I know I need 4 doses in 1 day. Because now what happens, look, your days cancel. And now we have milligrams per dose. And that's what the question wants. How many milligrams at each administration? Now we're going to do sig figs. Looks like we should have at the very end 3 sig figs governed by the 63-pound child. So 1430 milligrams per dose. That last 0 obviously is not significant. Temperature scales and conversions. So we have 3 different temperature scales. Fahrenheit, which you are very familiar with, Celsius, and then Kelvin. Kelvin is the SI unit. It's an absolute scale. So the kinetic molecular theory, it's called, that's centered around what's called 0 Kelvin or absolute 0, using gas law stuff. We see Fahrenheit all the time with weather. you turn on the news and watch the weather, it's always in Fahrenheit. Your phone probably has it in Fahrenheit. It's not used at all in the medical field. Celsius is what we use a lot worldwide. Important Celsius values for body temperatures down here. So a normal body temperature is 37 degrees Celsius. This cannot vary much or you will get sick, as you'll see here. If it goes too low, something called hypothermia, and that's if it's less than 35 degrees Celsius. If it goes too high, you could have heat stroke, and that's if it goes above 40 degrees Celsius. So there's not too much variation that you can have here. So you can see at the bottom Fahrenheit, Celsius, Kelvin, and then what normal body temperatures are across the board. So in Fahrenheit terms, about 98.6. Equations. So you can find all different kinds of equations with fractions and different things like that. I think the best one to use is this, and it's degrees Fahrenheit equals 1.8 times whatever your degree Celsius is plus 32. And that is used to go from Celsius to Fahrenheit and Fahrenheit to Celsius, that one equation. If you're given Celsius, you can just plug that right in for here and do your math. If you're given Fahrenheit, you could just plug in there and then solve for C. So you would subtract 32 and then divide by 1.8. So just one universal equation. You'll see other things using 5/9 and 9/5 and plus 32 and minus 32. I think this is the cleanest and the easiest. And then if you want to get Kelvin, notice there's no degree sign on Kelvin. It's just K, capital K. You take your degree Celsius and you add 273.15. That number does not change. That is a constant. You cannot go directly from Fahrenheit to Kelvin. You need to go to Celsius first. While traveling in Switzerland, you feel ill and visit a health clinic. Your temperature is 38.2 degrees Celsius. Do you have a fever? What is your body temperature in degrees Fahrenheit? Well, remember, your normal body temperature should be 37. So yeah, you have a fever. It's greater than 37. You have a fever. And then what is your body temperature in degrees Fahrenheit? We will use our formula here. And we're going to plug 38.2 in for Celsius. Order of operations. Sig figs, looks like we need 2 of them. So it should be I get 100.76. So with sig figs, I'm trying to find my key, make sure that math is right. Should be, yeah, 100.7, but really that's not right. That should round up. That should be 100.8. And that's degrees Fahrenheit. So next, it says many birds have a normal body temperature of 106 degrees Fahrenheit convert this into degrees Celsius. So we have our equation, and we would plug in 106. And then it's just an algebraic equation where you would subtract 32 on both sides and then divide by 1.8. Subtract 32, what is that, 74 equals 1.8 times C. And then divide both sides by 1.8. And you get 41.1 repeating. Sig figs wise, looks like we need 2, so we would get 41 degrees Celsius. And then it says convert that into Kelvin. So remember, for Kelvin, we just take our degrees Celsius and add 273.15. When we do that, addition, we're looking to the right of the decimal point for sig figs. 41 does not have any, and 273 has 2, so we go by the least. We do not want any. So we would have as our answer 314 Kelvin.